Hi, guys. I guess I'm just admitting all the other students for our class here. Give me a sec. Okay. All right, great. So a couple things I want to announce. I'm going to post these. I'll make an announcement for our class. We have a TA for our class. His name is Caden Prideaux, but he goes by Finn. And he's got office hours Mondays and Tuesdays from 9 to 10:30. He's got a Zoom link for it, which I'll post on our announcement page. Also, I got an email from the university saying that they've set up peer tutoring now. I know that this class is acceptable for peer tutoring. I think it's on like a list of classes. And you go to sign up for it on the student hub and they'll help set you up with that. I don't have any other information about that except the email that I got, but you can go ahead and take a look on your student hub to sign up for peer tutoring. But I'll post these onto our announcement page so that you guys can have that there. So today we're going to finish up. We have an example to work through for chapter 1.2 and admit middle. And then we're going to start on chapter 1.3, which is about limits. And we're going to basically spend the whole week on chapter 1.3 because it's such an important chapter. We want to make sure that we have it. Before I get started on chapter 1.2, does anybody have questions on the homework for 1.1 and 1.2? We would have had those, you guys maybe had hopefully started those over the weekend. Remember, those are due on Thursday, and also they'll be the basis for our quiz on Thursday. The Thursday quiz availability the window will start becoming available at noon, and it will go for 24 hours until Friday at noon. So kind of keep that in mind. We'll talk about that on Wednesday. So you guys have any questions on the homework for 1.1 or 1.2? I can go over a homework problem or two, unless the homework problem is really long. Let's see, hang on a sec. Do we turn in the homework on Canvas? Yes, it's a great question. So you will need to turn it in on Canvas. Now I have set it up on Canvas so that you will submit your homework as an assignment. I believe I have it listed by week, but it should be on our assignments page. And it's listed as a submission, online submission, so you can submit either a PDF. PDF is what I prefer. I'll be really upset if I don't get a PDF. I will take a JPEG if you don't have the ability to do a PDF, but I think that like most phones have like a free app that you can download that'll allow you to convert like a picture from your camera to picture from your phone to a PDF, and I'll take those. Now I don't know exactly how you do it on Canvas. This is my first semester working with Canvas, but I believe under the assignments you should be able to upload that. If you have any questions about it, you can send me an email with your assignment, but really try to upload it to there so that I can go ahead and grade it. Yeah, so that'll be due. I think it's set up to be due on Thursday at midnight. The homework is. But remember, if you only finish part of it, I'll give you partial credit, and then you'll have other opportunities to pass it in to get the full credit back. All right, so let's see, 44 on 1.2. Number 10 on 1.2, do we get to know the answers to these homework questions before the quiz? Yes, so that's a great question. Do we get to know the answers to these homework questions before the quiz? The answer to that is that if you guys ask me to go over the homework problems, I will absolutely go over them. I'm not going to post the solutions to the homework until probably before the exam, because I want you guys to have a chance to go through it, okay, to actually try it yourself. But you can come to office hours and ask me questions about the homework, and we can go through it exactly, okay? We can go through a couple problems at the beginning of each class, and then you guys can get a feeling for how you're supposed to be doing the problem. And I'll work it through exactly so that you'll have the answer for that problem. But I'm not going to post solutions to the homework before the quiz, okay? But I will post solutions to the homework before the midterm exam so that you guys can have that. Let's just go ahead and order. So chapter 1.2, 1.2 question, what was it, 44? Let me see, what's the question asking? So 44 says, let's see, it's come to describe horizontal and vertical coordinates of a particle as two separate functions. Oh, it's parameterization. In this case, horizontal velocity is the IROC. Okay, vertical. Calculate instantaneous horizontal and vertical velocities. Okay, so this is question 44 on chapter 1.2. 1.2, question 44. Okay. So what they're saying is we've got a position function, and it's written out like this: t, 3t plus 5. Okay, now what we've done here, maybe some of you saw this in a pre-calculus class or in a calculus class, but it's basically written out as a parameterization so that the horizontal position, right? So my x of t, my horizontal position is my x, what would be like my x coordinate, right? So my x of t is t, that's equal to that function. This is my horizontal. My y of t, my vertical position is 3t plus 5. Okay, I think, I'm trying to remember in this class, I think we do a little bit of how we talk about converting from functions to parameter representations. So now they're asking on this problem, what's the instantaneous horizontal and vertical velocities for this problem right here? Okay, which means that we're going to take, right, our instantaneous rate of change for this function. We'll take the instantaneous rate of change for this function. We're going to operate on them as two separate functions. Okay, so that means I'll just draw a line down here. So I'm going to take the IROC of x of t to get my horizontal velocity, okay, which is going to give me, I'm going to work it like this. So my limit as h goes to 0 of, this is going to be x of t plus h minus x of t all over h. Okay, so my horizontal. So the limit as h goes to 0. So I'm going to go t plus h. Everywhere I see a t in my x of t function, I'm going to plug in t plus h. So it's going to go t plus h minus t, all right, because this is just my x of t function, okay, which is going to give me t plus h minus t, right? T plus h minus t is just h over h, which is equal to 1. So this is, I'm going to go the limit as h goes to 0 of 1 is equal to 1. So my my velocity, my horizontal velocity, right, is going to be equal to 1. We're going to do the same thing for my vertical. Okay, we're going to do the IROC, the y of t, which is going to look like the limit as h goes to 0. This is going to be y of t plus h minus y of t all over h. Okay, so my y of t function is this right here, right? All I did was pull it out of my parameterized function here. So I've got just my y component. So I'm going to plug that in. So limit as h goes to 0. So everywhere I see a t on this function here, I'm going to plug in t plus h. So 3t plus h plus 5 minus 3t plus 5 all over h. So I have to distribute the negative to both of these terms here. So be really careful that you don't neglect one of your negatives there. Okay, so this is going to look like the limit as h goes to 0. All right, so this is going to be 3t plus h plus 15 minus 3t minus 5. Okay, so then ultimately when I do this and I clean it all up and I can subtract out, I'm going to get this thing is equal to 3, which is equal to 3. I skipped some of the algebra steps. So then my total IROC of my p of t is equal to 1, 3. And we just handled them separately as two individual functions. Okay. Question 10, 3, okay, question 10. Let me take a look at question 10. Given the position function and feet of particle traveling, in each case, okay, all right, we can work through question 10 as well. Let's scroll up just a little bit here. This is still chapter 1.2. This is question 10. Okay, so question 10, it says that we're given the position function x of t. So I'm going to write that down. X of t equals 1 over t. Okay, and then this is in feet for a particle traveling along the x-axis. So this is our positions in feet. Our time is in seconds. Okay, we want to be able to calculate the velocity on here between t and t plus h. So what we're doing is we're going to take the limit as h goes to 0 of, this is going to be x of t plus h minus x of t all over h. This is our definition of the derivative. Now, in case you've had calculus before, you've learned, the power rule, you've learned some of the shorthand rules. In these early chapters, and especially if you're told to use the definition of the derivative, you must do it this longhand method, okay? You can use in your mind or on a scrap paper your power rules and others to help you decide if you've done the right thing or if you've made an algebraic mistake, but you must use the longhand method because our shortcut, like the power rule, actually comes from, right, this taking the limit of our average rates of change. Okay, so what we're doing, we've got our average rates of change, I've got a secant line, right, but taking the limit, I'm basically bringing that secant line right up on top of my tangent line. So that's why we're doing this. It's like the longhand method, but that's really where our shortcut methods come from. Okay, so let's go ahead and plug that in. X of t equals 1 over t. So I'm going to do it from here. It's just going to look like the limit h goes to 0. So everywhere I see a t, I'm going to plug in t plus h. So I'm going to get 1 over t plus h minus 1 over t all over h. Okay, now watch what's happening. I have to find a common denominator between these two, combine them together, okay? And then this actually here, I'll write it out orange here. This is a fraction. We can think about this as a fraction which is h over 1. So I have to find a common denominator and then combine, right? And then I have a fraction divided by a fraction, so then I have to combine my numerator and my denominator, okay? So that's going to be a fraction divided by a fraction. So let's go ahead and we're going to do that algebra there, right? So when I go ahead and put that together, let's see, it's going to look like the limit as h goes to 0, right? So my common denominator is just basically the product of each of these two here, right? So that's going to look like t minus t plus h all over. Now I've divided by h over 1, right? So which is going to give me h times t plus h, right? So now this here is going to look like t minus h, right? When I distribute that negative, make sure you're careful. It's a common mistake. People forget that they have to distribute this negative here to both terms, right? So that's why I always put things in parentheses first, because otherwise I might forget that I have to distribute that negative to both terms. This becomes t minus h, which looks like the limit as h goes to 0 of minus h all over h times t plus h. Right, so I can cancel out this h and that h, they cancel. So then I'm left with, goes the limit as h goes to 0. Let me write this down here. The limit as h goes to 0, right? I've canceled that out, so there's a minus 1 in the numerator, t times t plus h. Now watch what happens. Now as h goes to 0, it's actually an h, I can plug in 0 for here, right? So this becomes 1 over t times t plus 0, which is equal to, when I evaluate this limit as 1 over minus 1 over t squared. So if you've had calc before and you've done like power rule or you've taken derivatives already, you'll recognize this as the derivative for that, okay? But in chapter 1.1, 1.2, and if you are told specifically to use the definition of the derivative, you must go through this long process of all the algebra. If you jump right to the power rule and you do that instead, you will not get credit. And I have to forewarn you, because we will have a question on the final exam where we're given some function like this and we're told specifically use the definition of the derivative to solve for the instantaneous rate of change, say for example. And you must show the limit as h goes to 0, this whole step. This is why I always write out this whole step first, right? This is my process. This is what I'm going to do. And then you have to show this one. You have to remember, you have to show whoever's grading it that you recognize, right, that you're plugging in t plus h, right, here, and then I'm going to go minus, and then I'm going to basically do a bunch of algebra to find out what my actual derivative is, my IROC. Okay. See, 11, 14, 42. So I think 11 is similar to question number 10. So I'm going to let you try to work through 11. 11 has a little bit more algebra, but it's really similar to question number 10. Let me see, what's question 14 look like? Okay, so then, and then 14, so here, so on question 14 says, we have to find the acceleration. So if this is the position, then we found the velocity, right? So I think if this is our velocity, right? So then question 14 is going to be taking the derivative of this. So the acceleration is going to equal to the derivative of the velocity. So question 14, let's see, I'll give you the answer so you can work it through and take a look at it, but I encourage you to go through the same process. Same process as question 10, but the answer, when you do this, so you can check your answer to see if you did it right. I got the acceleration was equal to 2 over t cubed. But you'll want to go through, this is just the answer so you can check to see if you did it correctly. Okay. 42. 42 is an interesting question. So what I can do is just, so 42 says we've got demand for a product in terms of number of consumers. So we're given the demand as a price S. And then they were asking about part C. So this actually is a pretty long question, but what I will do is I'll actually post the solution for it. So let me see, chapter 1.2, question 42. I'll post the solution for that up on our Canvas page, okay, so that you guys can see how that works out, because it's going to take too long for me to actually work it through, and we won't have time to go through things in the rest of the class. But I will post that solution for question 42. I'll do the whole question, and then that way you can see what 42 is going to look like. That'll answer part C. And my other class I had teach, same class, but at 8 o'clock in the morning, they asked for question 46 on chapter 1.1. Which I'll also post that on our Canvas page too, because they probably you guys will have a question about that as well if you get to that point. Okay. All right. I encourage you to, if you have any other questions, you know, about the homework, to please, you know, come to office hours, and then we can work through the homework problems. And I'm more than happy to answer, you know, questions that you might have about the homework problems. Okay. All right. So with that said, I will post those later. We'll do that. So let's do this. All right, so I believe we left off, the last thing we needed to do was to talk about example 4 on chapter 1.2. Example 4 is interesting because it's a similar process involving taking the limit of our function, right? The limit is h goes to 0 in order to find our derivative. But in order to work through the algebra, we need a trick, an algebraic trick on helping us how to solve it. So this whole problem here, the process is the same as what we've been doing, but I'm going to show you what the trick is, because I'm not sure, I think you may have a homework problem, something like that, but you'll want to make sure you have tools in your toolkit to answer it. Also, I want to mention too, I think somehow the comma got didn't get carried over, but there's a comma in here. So our function is just this 1 over t cubed plus 1 inside the radical, and then this t greater than 0 seconds, that's just something telling you about it. But there's no, we're not multiplying by t, just so that you know, okay, when you look at it. Okay. So we want to know, given the position, what's our instantaneous velocity at any particular time t? All right, so let's just write down, we're going to take notes for ourselves. So our velocity is going to be our derivative of our position, okay, which our definition of the derivative is the limit as our h goes to 0 of p of t plus h minus p of t all over h. Okay, it's going to be really helpful for you to write this down each time you do it, because it'll help you keep track of the process that you need in order to go through these things. Okay, so let's do this. So here's our p of t. So the first one, t plus h, everywhere I see a t, I put in a t plus h. Okay, so that means I'm going to go, don't forget your limit. Limit as h goes to 0, right? So this is going to look like this. 1 over t plus h cubed plus 1 inside of a radical minus p of t, which is this whole thing here. So 1 over t cubed plus 1 radical. And then all of that is over h. Okay. Whew. All right, so let's think about, I'm just going to write this out like this. This is h over 1. Okay, because ultimately I've got a fraction over a fraction, and I'll need to bring those together. Okay, so my goal is I need to be able to, evaluate my limit. I have to be able to plug in 0 for h, but I've got an h in the denominator, and there's no real easy way. If I FOIL this out, I'm still stuck with stuff inside of a radical. How can I combine these things here? All right, so the steps I need to think about, I have to find a common denominator. So the first step is I'm going to find a common denominator. Common denominator between these two here so that I can combine these, right? So my numerator becomes one fraction. To combine our numerator terms. Okay, then I want to be able to combine my numerator fraction with my denominator fraction into one fraction. So I'm going to combine numerator fraction and denominator fraction into one fraction. Okay, so right, my common denominator is just going to be the product of these two here. Okay, so it's going to look like this. So my limit as h goes to 0 is going to look like plus 1 radical minus t cubed plus h, oops, sorry, t plus h quantity cubed plus 1 inside the radical. Okay, all over, right, so I've just combined this here is a fraction divided by a fraction h over 1, which puts our h here, and then my common denominator, t cubed plus 1 radical times t plus h plus 1. There's a lot of algebra. Okay, so this is, I've just done these two steps here. I've skipped some of the algebra. There's algebra to get to that step. Okay, so now, and then this is just t plus h quantity cubed. So now I still can't evaluate my limit. I can't plug in h equals 0 here because look at it divide by 0, and I can't combine anymore, right? Because I think they're inside of a radical, so foiling things out and combining like terms isn't going to do me any good. So I need a trick. I need a trick in order to work it. And the trick is using this right here. I'm going to multiply this whole fraction by the conjugate of this term right here. I'm going to multiply top and bottom by the conjugate. Okay, once I multiply by the conjugate, and we'll talk about what that looks like, then I can start combining like terms. So let's go ahead, I'll write out what that conjugate looks like. So the limit as h goes to 0, I'm going to just rewrite this and then I'll multiply by the conjugate. So t cubed plus 1 minus plus h quantity cubed plus 1 all over this whole thing here. So h radical t cubed plus 1 times e plus h quantity cubed plus 1 here times. Okay, so here's our trick. I'm going to do this here. So my conjugate is this plus this. Okay, so this term here, so it becomes t cubed plus 1 radical plus e plus h quantity cubed plus 1 all over t cubed plus 1 plus e plus h cubed plus 1 radical, right? It's the same term, top and bottom, which means I'm just multiplying by 1, but it's going to allow me to rearrange. Okay, so watch this. These get multiplied out. I'm going to FOIL these out. So first, outer, inner, last. Okay, and what that will do is that'll get rid of my radicals, right? And then I've got this all multiplied out straight across the bottom here. Okay, so we'll write that out. So lots of algebra and combining like terms. And simplifying. Okay, I'm going to skip all the algebra steps, the mini steps, right? And I'll leave that up to you. I encourage you to go ahead and try it just so that you get accustomed to thinking about what it looks like. But I'll write out what it is. So if I do the foiling, right, and then I combine all the like terms, I'm going to get minus 3t squared h minus 3t h squared minus h cubed all over h times all this stuff here. T cubed plus 1 times t plus h cubed plus 1 times t cubed plus 1 plus e plus h cubed plus 1 radical there. Okay, phew, it's a lot of stuff. Watch what happens. There's an h here, there's an h here, there's an h here, and there's an h there. Okay, so I can factor out that h, and I can cancel them off. Okay, I'm factoring out the h across the top, and I'm canceling it with that h right there. Okay, so it's going to look like this. The limit as h goes to 0, and I'm left with minus 3t squared minus 3th minus h squared all over all this stuff here. So let's write it again. Q plus 1 t plus h quantity cubed plus 1 inside of a radical times, there's an addition here, so t cubed plus 1 plus t plus h cubed plus 1 here. Okay, phew, we're getting there. Okay, now what I can do is I don't have to multiply this out just yet. Okay, I can evaluate my limit. I don't have the h's that I have in the denominator. Okay, we're just going to make this a little more simple, but it's not going to give me a divide by 0 error. And if I plug in h here, right, what am I going to get when I evaluate this limit? Evaluate the limit. So we're going to get my velocity. This is a position function, so my velocity is equal to, right, the h's go away because I'm plugging in 0, so minus 3t squared all over, let's write this down. So this is going to look like t cubed plus 1 times t cubed plus 1, right, because that h going to 0 is going to make that just t cubed plus 1 all over t cubed plus 1 plus, t cubed plus 1 there. Okay, now I can leave it like this. When in doubt, you can leave it like this. Or I can multiply this out, right, and combine. Okay, in my denominator, and what I'm going to get is minus 3t squared all over 2 t cubed plus 1, the 3/2, and this is in meters per second. And that's my velocity. That's my derivative. E of t equals. Okay, but the trick, this is the whole point about going through this whole problem, isn't to torture you with all these radicals and all this algebra, right? But it's to show you the trick, right, of multiplying by the conjugate, right, which is right here. Top and bottom, same thing. So I'm just rearranging stuff, but there's a lot of algebra that I did offline, and I'm just showing you the solution. But I encourage you to go ahead and practice that algebra so that you can see, and then you'll have the solution for all the little subsequent steps. Okay, and that's our velocity. Yeah, should we finish example 3b in last class? Yeah, that's a great question. So I think 3b was the equation for the tangent line for that particular problem. What I'm going to do is I'm going to work that offline, and then I'll post that example 3b, and I'll post that on my example pages, and then I'll scan it all in and I'll post it to this chapter 1.2. I'm going to put the solutions for the lecture examples in week 1 because that's where I first posted the lecture examples. You guys can go ahead and take a look for that later today. The lecture examples for chapter 1.1 were posted last Thursday. If you guys want to take a look for those too. Okay, but I'll work through that particular problem 3b on 1.2. I'll do that on this page here, and then I'll post it. Sometimes you don't have time to do them all, but I'll at least give you the solutions for them. Okay, you guys all done? Anybody need more time writing this down before I move the page and then start something different? You guys good? So I'll scan that in and I'll post that later. Okay, all right. Exciting stuff. We're going to start chapter 1.3, which is about limits. And like I said, we're going to spend several days on this chapter, so don't sweat it if, as we're working through it, things aren't quite coming together. We're going to answer a lot of different questions and work through a lot of different examples for this chapter. So by the end of chapter 3, right, you guys will, by the end of chapter 1.3, you guys will be very adept at looking at limits and evaluating, you know, whether it exists or how do you solve it. Okay. Also note too that our quiz on Thursday will contain the stuff like the early parts of the homework questions for 1.3, but obviously not everything for 1.3 because we won't have covered everything for the quiz, but it will contain a little bit of limit stuff. All right, so let's go ahead and get started with thinking about it. So we're gonna kind of work through these using examples, but let me see, where's my lecture examples for this? Give me just a second to find my lecture examples for section. It looks like I printed out 2 copies of that. It looks like I didn't print out. Let me do a really quick printout of. Let me do a really quick printout of my lecture examples for that because it looks like I didn't print out. For that. Give me just a second. I'll print that. Okay. Here. And there. Great. Okay, so let's go ahead and get started while that's printing out. So, so limits. Okay, so one of the things that we want to ask ourselves is this. So our question, when we think about limits, is going to look like this. We want to say, how do the values of our function we'll call our function f of x. How do the values of f of x behave when x, our inputs, when x approaches a number, some number c, right? So along, we've got, you know, within our function, we've got our domain, right? As x approaches some value along that, what's our function doing, right? And this is gonna, we're asking this question whether or not f of c is defined. Okay, so our question, right? So we want to know, we've got this function, it's doing something, has some kind of behavior, and then as x is approaching some value along the domain of that function, what's our function doing? What's the behavior doing? And we're not even looking exactly at what's the function equal to at that particular spot, see, right? We don't even really care so much, but what's happening to the function behavior as we approach it? Okay, so let's go ahead and think about our first example. So looking at the lecture examples for chapter 1.3, and I've got this function here, f of x equals sine of x over x, where x is in radians. And I want to point out, make sure on your calculators, right, when I do this, my mode, right, my mode is set to radian. If your mode's set to degree, when you go to plot it, it's going to look like garbage. Also, when I go to plot this, if I do sine of x over x, I'm going to be really conservative about my parentheses. So I'm going to say sine of x. Make sure you close that inner parenthesis, and then I'm going to say divide by x. Okay. So I'm making sure, I'm just being really conservative. I may not need these outside parentheses, but I'm not sure. I want to make sure my calculator doesn't do sine of x over x, which would just be 1, sine of 1. I want it to do sine of x divided by x, and I want to graph it out. And it's going to give me a function that looks something like this. Okay, and we're going to plot that as well. So now we know, just make sure also, you can be sure that everything that we do in terms of trigonometry is in terms of radians, okay? So all your answers, if you're ever asked to come up with an answer for things, sine of something or cosine of something, it should be in radians, okay? So, but just make sure when you go to graph it out that your mode is set to radians. So I'm going to just do a quick plot of that. Here's my x, here's my f of x, right? And it looks like this was about pi, that was minus pi, and this is equal to 1. Now my function, it's doing stuff, it's gonna come up to here. And then we know, right, when x is equal to 0, it can't be, I have a divide by 0, so I'm gonna put an open circle there. And then my function cuts down like this, and then it, you know, does stuff, it goes on. Okay, so this is just kind of a really loose graph. I like the graphs because it helps me visualize what's actually happening. So let's think about it. My function, f of x equals sine of x over x. Now the sine of x sine of 0 is equal to 0, right? So this is at 0, I'm looking at, so let's write it. So f of 0 is equal to sine of 0 is equal to 0. Obviously, x is equal to 0. So 0 over 0, this is undefined. Okay, we're going to talk more about what we need to do here, but this, right, I've got to divide by 0 problem. So my function, I've got to divide by 0. It's undefined when x is equal to 0, but I want to know what's the function behavior at that undefined spot. That's the interesting thing. As x approaches 0, what's this function doing? So let's write this down both in English and in math so we can start learning how to read these math equations. So when I say x approaches 0, right, I write it like this. As x approaches 0, you don't have to write it in English. I'm writing it in English so that you can see, right? This is, when you read this, you're going to read it in your mind like this. X approaches 0, okay? So now when I do x approaches 0, I have to think about x approaching 0 from both sides, from the right-hand side and from the left-hand side, okay? So that's part of our evaluating of limits. We're going to go through this systematically, but I'm just kind of introducing this concept. So if I'm approaching, I write it like this. This means I'm approaching 0 from the right-hand side. It looks like a plus, right? X approaches 0 plus means I'm approaching 0 from numbers that are just slightly greater than 0, okay? So as my x, it's like I'm coming, as x is going this way, this is our 0, as x is going closer to 0, right, my function's going closer to 1. You can do it from the other side too. It looks like a negative, so x approaches 0 from the left. Okay, which means x is coming in this way. So here's 0. X is coming in this way. My function is approaching 1 from the left-hand side. So I'm looking at what's my function doing from the right and the left-hand side. I need to evaluate both sides. Okay, so I can write this out like this. The limit as x approaches 0 of our function, right? I can see it here. As x approaches it from the right, it goes to 1. As x approaches it from the left, it goes to 1. This thing equals 1. We're going to go through all this. It's just an intro example. We're going to go through all this very systematically so you can see how we got this number and what does this all mean. So don't worry. This is just kind of a high-level example to kind of get you thinking about what's going on. So we can write this out in English by saying stuff like this. F of x approaches 1, or I can write f of x converges to 1 as x approaches 0. Okay, both of these are correct ways of writing it. Now, this is what you would put down on a quiz or a homework or a test, okay? This, I'm just writing it out in words so that you can see how we read this math equation, right? So as x approaches 0, the limit of f of x as x approaches 0 is equal to 1, right? Means my function converges to this value here, okay? Or you can even say my function approaches 1, okay? We're going to talk about what all these things mean, okay? I guess I'll have that first example. Anyone need more time writing? All right. So let's go ahead and do some definition here. So I'm going to define limit, right? So I'm going to say, let's assume that our function is defined for all x in an open interval. Right, I've got some, range of values that make up my domain. Okay, so my function is defined along my domain. This is how we say that. It's defined for all x in an open interval. And that interval contains the number c, which is just some number within that interval. But the function itself may not be defined at c, okay? But not itself, which is another way of saying that f of c may not be defined. Like in our last example, oops, may not be defined. Okay, and our last example, x approaches 0. 0 was within that open interval of all real numbers, right? But our function itself wasn't defined at x equals 0, but we were able to still work through the limit. Okay, that's all we're saying right here. Okay, so we are going to say, so we say the limit of our function f of x as x approaches c is equal to L. I'm writing it in English, and then I'm going to write it in math so you can see what that looks like. So writing it in math looks like this. The limit as x approaches c of our function is equal to L. This, the math, is what you would write down as an answer. This here is just so you know how to read it when you look at this. The limit of f of x as x approaches c is equal to L. Okay. We can think about it like this. F of x minus L, okay, is going to get really, 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 really small. It's going to become almost nothing. Okay, that means that our limit, right, of f of c minus L is going to be equal to that, these values here. Okay, so now I can say conversely, if the values of f of x do not converge to any limit as x approaches c, we say that the limit as x approaches c of our function f of x does not exist. How do we think about this? How do we know if the limit doesn't exist? It's a whole topic that we are going to cover. We're going to cover all the different aspects of the limit not existing, okay? So I'm putting this out there as part of our definition, and then we're going to go into great detail this week in chapter 1.3, talking about how we know, does the limit exist or not? What are our criteria for it existing or not? Okay. Also, we need to note that the value of our function evaluated at c plays no part in evaluating this limit. Okay, doesn't play any role, right? I mean, think about it. I can define a function, that first example that we did, sine of x over x. Okay, as x approaches 0, I can say when x approaches 0, this function is equal to 10. I can just arbitrarily define it, okay? So, but I want to know what's the behavior of my function as I approach x equals 0, right? So as x is approaching 0, what's my function doing? I don't care what the function is actually equal to at that number. I want to know what's the behavior on either side. We're going to go through a lot of examples like that so that you guys can see. Anybody need more time writing this stuff? Okay. So we have a couple extra things here. There's a theorem that says we've got these constants, A and C. Okay, so I can say part A is the limit as x approaches some c value of k equals k. We're going to do an example just on that so you can see. And then part B says the limit as x approaches c of x is going to equal to c. We're going to do example 2. Actually does both of these here, and we'll graph it out to show you what it looks like. So now example 2 looks like this. This one is like part A, the limit. I can think about f of x equals 5. F of x equals 5. That's like if I graph, right? I've got, this is my x, this is my y. 1, 2, 3, 4, 5. So my line y equals 5 is like this, right? So 1, 2, 3, 4, 5. So as x approaches 7, right, my function is equal to 5. Okay, so my function is equal to 5 no matter what, right? It's just that's the function. Here, 3x plus 1, okay, this is just my line equation, right? So it's going to look like this. This is my 3x plus 1. As x approaches 4, what is my function equal to? I can just substitute 4 in for x right in here. So I go 3 times 4 plus 1. this thing is equal to 13. I've just substituted. I don't have any problems where if I just do a raw substitution, I'm going to get a divide by 0 error or any kind of thing that's going to cause this to bomb out. So I can just substitute and do a regular evaluation. Okay. So let's start talking. Example 3, we're going to talk about the steps that we need to do for example 3, and then we'll start working through it. So some steps for preliminary steps for thinking about how we're actually going to be evaluating limits. And this is how we start to kind of develop this intuition about how I think about limits and what I need to do. So we're going to approach first off from the left and the right, okay, values of x, and we'll find out what our values of y. So the first thing is I'm going to make a table of values of f of x, okay, based on values of my input, or x values that are close to but less than c. So I'm going to go x is approaching c from the left-hand side. So if we were approaching 1, but I'm going to approach it from the left-hand side, I'm going to look at values that are just a little bit less than 1. So 0.9, 0.99, 0.99999. I'm going to get really, really, really close to 1, but without equaling it or going over it. Do the same thing approaching it from the right. So I'm going to make a table of values of f of x for x close to but greater than. So we're going to, x is going to approach c from the right-hand side. So if x is approaching c from the right-hand side, I'm going to look at values of 1 that are just slightly bigger. 1.1, 1.01, 1.001, and so on and so forth. And I'm going to get really, really close to 1, but I'm not going to equal it or get less than that. Okay. Now what I need to do is I need to compare as I'm getting closer and closer and closer to that value, my c value. Are these two things like equaling each other? Are they converging on the same number? Or are they like going off in completely different directions? So we're going to compare both tables. So if both tables show our function approaching the same number, L, then L is the estimate L is the estimate of our limit. We'll work through an example. We have time to work through example 3 so we can see what that looks like. We'll actually go through the whole process of making a table. You guys need a minute to finish that? Okay. So looking at example 3, I've got this function here. And I always like to come up with a graph just so I can visualize it. You don't have to, okay, but I find it very helpful. All right, so I've got 3, 6. So my function goes like this. Here. This shouldn't be so disjoint, but basically, you can imagine, right, as x approaches 9, well, radical 9 is equal to 3, 3 minus 3, that's equal to 0. So I have a 0 in the denominator when x is equal to 9. It's undefined. My function's undefined when x is equal to 9. So I want to be able to approach, right, I'm going to look at, as x is approaching 9 from the left-hand side and from the right-hand side, what's my function doing? What's the behavior of the function? So we're going to, let's write that down. So it's undefined at x equals 9. Okay, but that's the behavior. It's really, it's at the spots where it's undefined that are interesting. We want to find out what's going on there. Okay, so what I'm going to do is this. I'm going to say, I'm going to approach it first from the left. Right, and I'm going to say, let's do this. I'll put it over here. So from the left, so I'm going to go x approaches 9 from the left because we're looking at x approaching 9. So x approaches 9 from the left, and I'm going to write my function down here. So this is going to be x minus 9 all over radical x minus 3. So I'm going to choose values of x that are close to 9, but not greater than. So the first thing I'm going to get is 8.9. If I plug in 8.9 here, I'm not going to get a divide by 0. So I go radical 8.9 minus 3, 8.9 minus 9. I'm going to get a number. That number is that I got was 5.98329. I'm going to choose a value, 8.99. See how I'm getting closer to 9, but I'm not going over. And I plug those values in. Watch your order of operations when you do this on your calculator, you know, that you make sure you have parentheses on the top and the bottom so that you get the correct number. If I go even closer, right, I'm going to get 5.983, and I'm going to go even closer. Okay, so you can see what's happening, right? So I approached from the left. Let's write down, this is from the left. Okay, now we're going to approach from the right, and we're going to compare. So I'm going to go x approaches 9 from the right-hand side, and I'm going to do the same thing for my function. So this is going to be x minus 9, radical x minus 3. So I'm going to choose values for x that are close to 9, but just slightly bigger, and I'm going to plug them into my function. I'm going to get a value here. So let's just, so I did, first one I did was 9.1, and I got, when I plugged in 9.1 minus 3, I'm not going to get a divide by 0 for that, but I'm going to plug it in here, and I'm going to get, what I got was 6.01662. Then I did 9.01. I plugged that into here. 6.00166, 9.001, 6.0000167, 9.0001. Right, and this is 6.1234167. Okay, now look at what's happening, right? I'm going to compare, right? So I'm going to compare this one with this one. Right, if I compare these two, right, can we see what number it's approaching? On the left-hand side, it's going 5.99999. On the right-hand side, it's 6.00001. Right, so from either side, the left and the right, we're both approaching 6. It's like I'm going to take the average of these two, right? But in our mind, we can see that we're approaching 6. Approaches 6. Our answer approaches 6. Okay, so now I can write my answer is, I'm going to say the limit as x approaches 9 of my function x minus 9 radical x minus 3 is equal to 6. Okay, based on my table of values. The table of values is a really good first step, okay, for how we're starting to think about limits and how we work it through. Okay, it gives us a good intuition because we need to evaluate from the left and the right. Okay. Anybody have questions on this example here? We actually have time to do another example before our class ends. Anybody have a question on what I've done here? Okay, good. All right, so let's try example 4. So example 4 says, with this function, sine of limit as x goes to sine of pi over x. Investigate the following graphically and algebraically. I like to do graphically, right, so we can see what it looks like, right, and then algebraically is building that table. Okay, so we're going to do this. So again, right, this here is not defined at x equals 0, right? I'm going to get a divide by 0 error there. Okay, so I'm just going to come up with a function here. I'm going to graph it out. And this is the kind of thing, right? You actually want to use your pi button, right, when you go to graph this out. So I'm going to go the sine of, I'm going to put, sine of, right? And I'm going to do my pi button, pi divided by x, right? And then when I graph it, it's going to look like, and I'm actually going to zoom. Right, so this is what it looks like here. Okay, when you go to graph it, like I said before, make sure you're in radian mode, otherwise it'll be garbage. All right, so I'm going to draw out my picture, focusing on between 1 and 1 here. So my function comes in right at 1, and then it's going to out this, and then basically what happens is, and then it starts to oscillate like that. Okay, the graph, right? Don't worry, we're not going to be judged or graded on your graphs. Graph is for you to be able to visualize what's happening. Okay, I find it very helpful to have a picture of things. Okay, here's my X. Here's my Y. All right, so keep that in mind. This just can be a sketch. Okay, so we're going to do the same thing with the table that we did before from the left and the right. Okay, so I'm going to build up. I'm going to say X is approaching 0, and we're going to come from the left. Okay, you look at values, and I'm going to be evaluating sine of pi over X. Okay, see what I get. So I'm going to choose values as I approach 0. I'm going to go minus 0.1, right? So from the left means I'm in the negative range. So minus 0.1, which gives me 0. Minus 0.03. I'm plugging these into my calculator. 0.866 minus 0.007. Again, make sure you're in radian mode. So all these answers here are in radians. Okay. 0.007, I get minus 0.434. I plug in minus 0.0009. Then I'm going to get minus 3.342. And then minus 0.0065, and this is minus 0.95. Okay, so this is approaching it from the left. So we're approaching here from the left-hand side. Okay, we're going to do the same thing. I'm going to choose values as I approach X from the right. So X is approaching 0 from the right. I'm going to be looking at my function again, so sine pi over X. Okay, so my X from the right is going to look like 0.1, and I got 0, and I got 0.03. So I chose these values here, but they're positive now. 0.3, and I got minus 0.866, 0.007. I got positive 0.434. I can see a problem already. 0.0009 minus 0.342. And I'm going to go 0.065 and then positive 0.935. So this is approaching it here. Right? Okay. Now let's take a look at what's happening. Okay. As I approach, you can kind of see it from the graph view, but the algebra should line up the same. Okay. So as I approach, right? Look at. So this is the magnitude is the same, right? But look, this is negative, this is positive. That's positive, that's negative. Negative, positive. They're oscillating values. So as I approach from the left and the right, I'm looking at values that are opposite in sign. Okay, so these are, oops, sorry, you can't see what I'm writing, oscillating numbers. So I'm not converging on the same number. On that previous example, we converged. You can see, 5.99, 6.001. You could see it's approaching on the same number. It was approaching to 6. Here, I've got a negative and a positive. So I'm approaching, right, from the left and the right, I'm approaching opposite sign numbers. So I'm not approaching the same number. Oscillating numbers and not approaching same value. Okay, so that's a problem, right? If it's not approaching the same value from the left and the right, then our limit does not exist. Okay, so we would write that out. So I would say the limit as x approaches 0 of my function sine of pi over x does not exist. And the reason why is different values on left and right. It's oscillatory. Don't worry if it's not making a whole lot of sense. We're going to say it does not exist. Okay, that's our answer. Okay, now we're going to define. We have characteristics. We have reasons for why a limit does not exist. Very specific. Okay, we're kind of building up to those reasons now. We're building up to how we're going to be evaluating limits. Okay, we're going to at the end of chapter 1.3, we'll just summarize so that you can see all of those reasons that would make a limit not exist. Okay, so one of them is right. The left and the right don't equal to each other as we approach the same value. Okay. Okay, guys, I'm going to quit for today for that for this chapter section. Take a look at homework for 1.3, and then so you can come and ask questions about it on office hours or on class on Wednesday. Okay. Have a great rest of the day, guys. Bye.
Thank you.
Bye.
Thank
Take it
you.
easy.
Thank you.
Take care.